In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
Cosmic collisions. They are among the most violent and life-altering phenomena in the universe. From fender benders to high-velocity impacts, gravity is constantly moving everything around in space. And so things are bound to collide. Asteroids, comets, galaxies, and planets are some of the objects involved in these energized events. Yet, as violent and destructive as these collisions sound, we may owe our very existence to them. Darren Ragozine is on the hunt for answers to an ancient collision that happened far off in space. Ragozine has zeroed in on a vibrant gray rock. It's the vestige of an ancient fiery impact involving two massive objects, the largest being the size of Pluto. This gargantuan rock, called 2003 EL61, is a member of a collisional family that orbits just beyond the planet Neptune.
Collisional families are groups of objects that have very similar shapes, sizes, and tilts as they go around the sun. They stayed in a tight cluster of orbits because they came from the same objects.
Objects that came from the same parent should be made out of the same material. So by studying the compositions and verifying that they're similar, we can know that they came from the same origin.
Billions of years ago, 2003 EL61 and its family members were part of one gigantic body over 1,000 miles across. The mammoth object resided in the Kuiper Belt, a repository for objects that didn't become planets in the outer solar system. But at that time, the Kuiper Belt was buzzing with loose objects. The ice-covered rock eventually slammed into another object half its size, at a speed estimated at 3,000 miles per hour. The impact produced energy equivalent to 10 billion atomic bombs. It also ejected large chunks of ice from the object, each one ranging from 250 miles in diameter down to mere specks. The fragmented pieces are now all members of a collisional family, with 2003 EL61 being the largest piece.
We're here at a clay pigeon shooting range because the trajectory of the shards after a clay pigeon is hit is very similar to the orbits that family members take. Once it's hit, the pieces fly out, but they pretty much follow that same trajectory as they go down.
In the case of 2003 EL61, the impact has been sending it rapidly spinning like an amusement ride, rotating once every 4 hours.
It got hit sideways, and so it was spinning, and because it's spinning so fast, it elongates itself, pulls itself out, and it's shaped sort of like a football, except it's more like a football where you let out some of the air and squash it on one end. So 2003 EL61 is the fastest spinning large object that we know anywhere in the solar system. There's nothing else quite like this.
Planetary astronomer Mike Brown has conducted extensive surveying of 2003 EL61, the biggest and brightest known object in the Kuiper Belt.
It's bright, it's big, but it's also very shiny because we think when the collision happened, most of that ice got removed and the things around it, and it just left a little thin layer of almost pure ice sitting on top of this rock. And that's why it's so much shinier than everything else we see out there. It's that pure ice that's out there. I think that 2003 EL61 is the largest object out there that had a collision that formed a family. I really do think it's one of the largest collisions that occurred in the outer part of the solar system, in the history of the solar system.
The impact not only created 2003 EL61 and its galactic family, it also produced 2 moons.
We're searching for them now, and something like 10% of Kuiper Belt objects have moons. But all of these objects that we've looked at, only a few have more than 1 moon.
Infrared telescopes determine the size of these objects by measuring the heat they emit. Although 2003 EL61 is 100 times larger than its next biggest family member, this fragmented group maintains similar orbits.
The pieces stay together and keep following each other in their orbits around the sun. So astronomers can identify collisional families by looking for common orbital characteristics. So the distance from the sun, how elliptical the orbit is.
When you shoot a shotgun, the pellets go out into similar trajectories as the original object. This is the same as in collisional families in the solar system, which follow similar orbits after the collision as the original object was under. And this is how we're able to identify them. So after this collision happens, they are all in slightly different orbits. And like runners on a track, if they all stayed in their own lanes, if they all ran about the same speed, because the lanes have slightly different lengths, after a while, if you looked at the track, each runner would be at a different place along the track. And this is the same for family members right now. So even though they're not next to each other today, when we look at them, we can still identify each in terms of the way their orbits are, the way they go around the sun.
Scientists wonder whether 2003 EL61 could eventually be involved in another collision. It seems as though Neptune is gravitationally tugging on it, which will eventually change its orbit.
In 100 million years, it's going to just barely cross the orbit of Neptune. At that point, it's hard to guess what's going to happen. Neptune can either throw it into the inner solar system, or it can try to toss it out, or many different things can happen.
Objects are periodically bumped out of the Kuiper Belt and drift in the direction of the inner solar system. These icy rocks become comets as they form long tails of ice and dust when moving towards our sun.
Eventually, it will work its way perhaps to Jupiter. At that point, Jupiter actually throws it out of the solar system. No one has really thought about what would happen if something the size of 2003 EL61 hit Jupiter.
But smaller comets have been known to strike the gas giant. In July 1994, the Hubble Space Telescope observed an astonishing event. A string of comet fragments called Shoemaker-Levy 9 crashed into Jupiter at the speed of 130,000 miles per hour. The largest cometary piece released 6 million megatons of explosive energy. They impacted Jupiter about 20 times every 7 hours until they were destroyed. The points of impact left scars on the surface of Jupiter, reminders of the violent event. JPL senior scientist Don Yeomans has analyzed the Shoemaker-Levy 9 event.
The Shoemaker-Levy 9 impacts was an eye-opener for the public and the scientific community in the sense that these cosmic collisions do happen from time to time, and the energy that they can generate are just enormous. It's a good thing this thing hit Jupiter and not the Earth, because it would have been a serious problem on Earth.
Had the Shoemaker-Levy 9 struck Earth, it would have made devastating impact craters, the largest about 40 miles wide. Any one of them could have destroyed a metropolitan city and churned up enough dust to block sunlight for months.
Jupiter being in the outer solar system and being far more massive than any of the other planets combined takes a lot of hits that might have otherwise been destined for Earth. So Big Brother Jupiter is out there watching us.
Jupiter acts like a planetary goalkeeper, but will it be able to deflect 2003 EL61 if it breaks loose from the Kuiper Belt and tumbles toward Earth?
It's also possible that it could hit Jupiter like Shoemaker-Levy 9 did. This object is about 2,000 times bigger than the thing that hit Jupiter, than Shoemaker-Levy 9. So it would be an incredible explosion. In the night sky, it would be the single most prominent thing that you could see. It would be bigger than the full moon, at least the tail of it.
Because collisional families are difficult to locate, researchers are eager to study 2003 EL61 and its relatives.
Less is known about collisional families in the Kuiper Belt, simply because fewer Kuiper Belt members are known than we know about asteroids. So less research has been done to try to find collisional families within the Kuiper Belt.
As of today, we know of only this one collisional family in the Kuiper Belt. They're very hard to find and to recognize, and we got extremely lucky with 2003 EL61 and its family. We're working right now trying to figure out other ways that we might be able to find these additional families, because they must be there, but we just don't know how to find them yet.
Like these clay pigeon pieces, family members in the 2003 EL61 family all remain in similar orbits today. We're able to follow them today and to learn more about the history of the Kuiper Belt and of collisions.
One enduring mystery is when the 2003 EL61 collision actually occurred.
We think we can look at where the different objects are now and try to essentially run time backwards and figure out when they were in this one big collision. Our best guess is that that answer is going to be essentially at the very beginning of the solar system.
2003 EL61 and its family were probably created during one of the most turbulent periods in the history of our solar system, when collisions were as common as stars in the night sky. From the beginning, collisions have been a fact of life in space. They created much of our universe, and at the same time, destroyed some of it along the way.
Collisions are the way that you build planets. Without collisions, you don't have planets to begin with. You start out with very small particles. Each one of them collides together, bigger and bigger and bigger and bigger, until you slowly build up these planets. At the same time, collisions can destroy planets.
The planets in our solar system were created during a period called the heavy bombardment that happened over 4.5 billion years ago. And the collisions didn't stop with the heavy bombardment. Over 600 million years later, our solar system experienced another spike in collisions during a period called the late heavy bombardment. Stray rocks, too small to become planets, played interplanetary billiards, striking and bouncing off other bodies with tremendous force.
There were chunks of things flying everywhere, and so there were many, many, many collisions. A lot of the craters that you see on the moon were from that very early period, right when the solar system was still forming.
And our moon reveals just how volatile the period was on Earth.
We can even calculate to some degree, based on cratering on the moon, just how often we got hit by these rather large objects, say 6 miles across.
Towards the end of the late heavy bombardment, we do get asteroids hundreds of miles in diameter coming in and striking the planet. Those are certainly capable of vaporizing the oceans and leaving a tremendous scar where they hit, raising the surface environment far beyond the possibility of any life surviving.
When the late heavy bombardment subsided, approximately 3.8 billion years ago, objects that didn't coagulate into planets sought refuge in cosmic graveyards. In the outer solar system, leftover rocks reside in the Kuiper Belt. In the inner solar system, they collectively orbit in the asteroid belt. Like in the Kuiper Belt, collisional families have also been discovered in the asteroid belt. They're pieces of asteroids that originated from a larger object that was broken apart by a collision with another asteroid.
Collisional families in the asteroid belt result when one asteroid gets hit by another and breaks into pieces. The fragments actually stick together in their orbit around the sun, and astronomers can identify collisional families by looking at their distance from the sun is the same, the tilt of their orbit is the same, and the ellipticity, how squashy the orbit is similar. Also, if we see that the asteroids are made out of the same material, it's a good bet that they may have originated from the same object.
There are approximately 20 to 30 known collisional families in the asteroid belt. Scientists are keenly interested in one galactic collision that produced the Baptistina family, wayward fragments that originated as one single body, the size of Mount Everest. About 160 million years ago, this colossal rock was broadsided by another giant rock in the asteroid belt. The deep impact created a shower of smaller pieces, over 136,000 of them. Scientists estimate that 20% of the rocks escaped the asteroid belt, and 2% of them rained down on Earth. Some say there's a 90% probability that one of the Baptistina asteroids was responsible for the extinction of the dinosaur. 65 million years ago, a myriad of dinosaur species ruled the prehistoric world. But a catastrophic event wiped them off the face of the Earth. Now, scientists have good evidence of what happened to them. It's now been confirmed that a gargantuan cosmic object plummeted down from the sky and exploded in the Yucatan Peninsula near the modern-day Mexican village of Chicxulub.
We think it was an object at about 6 miles in diameter, coming in at about 12 miles per second, which would cause an impact energy of about 65 million megatons of TNT. Now, to put that in perspective, that's about one Hiroshima-type blast every second for about 140 years. It was really quite a hellish environment.
It's believed that this asteroid contributed to the mass extinction of over 75% of the species on Earth at the time.
What we think happened with the Chicxulub impact is you have a large asteroid coming in, it hits the Earth, and throws an enormous cloud of debris and dust into the atmosphere. This effectively screened out a large fraction of the sunlight. So imagine a cloudy day that lasts for years.
Amy Mainzer has investigated the rapid die-off of life as a result of the impact by visiting the Aquarium of the Pacific in Long Beach, California.
We can learn about the effects that an asteroid impact might have had on planet Earth by looking at this nice tank here. We see that it's full of color and life, lots of different species, many different animals and plants. Of course, this whole ecosystem depends ultimately on the sun. Big fish, like we see here, eat the littler fish. The little fish eat the plants, and ultimately the plants depend on sunlight to make energy through a process called photosynthesis. So you can imagine that if something happens that screens out the sunlight, all these beautiful animals will perish.
The apocalyptic event has been called the KT extinction because of a thin band of geological signatures dating to that time all over the world known as the Cretaceous Tertiary, or KT boundary. It separates the age of reptiles and the age of mammals. Dinosaur bones are not found below the KT boundary. Some say it's a good indicator that they and other species became extinct from the impact that blocked out sunlight for years.
We can get an idea of what might have happened to life on planet Earth following an asteroid impact by comparing deep water and shallow water marine systems. In deeper water, where there's less sunlight, there are fewer colorful corals, fewer types of colorful fish, and generally less species diversity overall.
Some scientists had been skeptical that an asteroid caused the KT extinction.
For a long time, people didn't really start to believe that asteroids could really hit the Earth and make a noticeable impression until the discovery of Meteor Crater.
Almost 50,000 years ago, during the Pleistocene period, a 150-foot asteroid struck Earth with the force of 2.5 megatons of TNT. The impact carved out 175 million tons of rock in what is now the Arizona desert. It left a giant bowl-shaped hole, which has been named Meteor Crater.
In fact, evidence proved that it had to have resulted from an asteroid impact. A scientist named Eugene Shoemaker found shocked quartz at the bottom of the crater, and it's only possible to get this particular kind of glass with extremely high temperatures and pressures generated in a very short amount of time.
By the 1980s, scientists hadn't found an impact crater linked to the KT extinction. But they had dug up other evidence. Iridium was procured from the KT boundary layer. Iridium is an element rare in rocks on Earth, but common in many asteroids.
It turns out that some asteroids are very high in iridium, and so they made the connection that this layer of iridium that occurred in a sediment layer some 65 million years ago was due to an incoming asteroid.
Even with the discovery of iridium, some still doubted an asteroid caused the KT extinction, until the 1990s, when a Mexican oil company found the smoking gun. While drilling off the Yucatan Peninsula, they discovered a 100-mile wide impact crater buried underwater beneath 3,000 feet of limestone. Analysis of the rock confirmed that the crater was in fact formed by an asteroid. And like Meteor Crater in Arizona, shock quartz or glass was also discovered at the KT impact crater site.
One of the other important lines of evidence for the impact at Chicxulub was the finding of shocked glass. This is basically when they looked at the impact site and in regions around it, and all around the world in fact, evidence was found of glass that was fused. It was basically created when the giant explosion fused it. And this particular glass type is really only found in the presence of an extremely large explosion.
Today, many scientists agree an asteroid caused the KT extinction 65 million years ago. And now some are trying to zero in on the exact asteroid that caused the event. Sediments procured from the Chicxulub site reveal the asteroid was a carbonaceous chondrite, a very primitive rock. These types of rocks have similar compositions to the Baptistina family, a collection of asteroids that once originated from a larger rock. So some say the odds are great that a Baptistina family member triggered the mass extinction that wiped out the dinosaur. Today, the Baptistina family could still pose a threat. Within the asteroid belt, its relatives span a region containing 2 gravitational hatches. These are areas where a slight nudge could boot an asteroid out of its orbital zone. it could send it soaring into the inner solar system, where it could slam into planet Earth. Cosmic collisions are not a thing of the past. They're ongoing and potentially deadly. Within the asteroid belt between planets Jupiter and Mars lives the Baptistina family, a group of rocks that originated from a larger body that was shattered due to a collision. After the impact, some Baptistina family members were ejected from the asteroid belt. It's believed that at least one eventually struck Earth 65 million years ago and caused the mass extinction of the dinosaur. And the KT extinction event may not be the end of the Baptistina family's wrath. Some say another relative could threaten our planet again in the future.
It's always possible that another member of the Baptistina family could make its way into the inner solar system and hit the Earth.
Researchers have been observing the Baptistina family. They've discovered that its relatives share similar orbits. But over time, a thermal effect called the Yarkovsky force is moving them into a danger zone.
The Yarkovsky force is a thermal effect on asteroids that has the ability to alter their orbits. When they get hit with sunlight, it takes a little while for the asteroid to heat up. This results in a thermal radiation that gives the asteroid a little push, which changes its orbit. The Yarkovsky force is not very big, but over millions of years, it adds up.
Over time, this gradual orbital shifting could produce another cataclysmic impact.
Simulations have been done to show that when these Baptistina family members happen to get into a resonance with the planet Jupiter, in other words, a resonance where the asteroid orbits 7 times for every 2 orbits of Jupiter, when that special moment happens, the asteroids can get shot into the inner solar system, just like hitting a flipper on a pinball machine. Some fraction of those asteroids are going to get into Earth-crossing orbits, which means they have a chance of hitting the Earth.
If an impact event happened anywhere on planet Earth today, it would destroy civilization itself.
Even if you managed to survive in a remote place, you would most likely starve. Humans would probably survive in a few places and recolonize, but civilization would collapse. These are civilization-killing events.
Future collisions could be hazardous to life on Earth, but the Chicxulub impact was a fortuitous moment for the evolution of humans. Research scientist Lou Ann Becker has spent her career investigating mass extinction events.
People say that if the dinosaurs had not perished, then there would be no people. Mammals would not have taken over if the dinosaurs had been so fortunate to have been able to continue to reign beyond the 135, 40 million years that they happen to be on the Earth.
Becker claims, like humans, dinosaurs also evolved after an epic extinction event, the largest in the history of planet Earth. It's the Permian-Triassic extinction, also known as the Great Dying.
It's also kind of ironic to me that if our theory is correct about the Permian, the dinosaur came in with an impact event and went out with an impact event, which is pretty interesting.
It's perhaps the ultimate cosmic cold case, a mass extinction unmatched in the history of the universe. 250 million years ago, long before the dinosaur ruled, smaller creatures and abundant plant life prospered on Earth during the Permian-Triassic period. Then, some mysterious event wiped out almost all life at that time.
In fact, is the most severe extinction with respect to how many different animals and plants perished. It's the biggest extinction event in the history of life on our planet.
Becker is on a mission to solve this prehistoric crime. Like the KT impact that probably killed the dinosaurs, she claims to have uncovered evidence that a giant asteroid also caused the Permian-Triassic extinction, which occurred about 185 million years earlier. During the Permian-Triassic period, our world was comprised of one supercontinent called Pangaea and a superocean called Panthalassa. According to Becker, a 7-mile-wide object slammed into the ocean near the southern tip of the supercontinent, which is now off northwest Australia.
If you were standing on the beach 250 million years ago, you'd probably have a pretty good view of this particular event. You have a large body the size of, say, Mount Everest, rigid body slamming into the continental margin along the actual beach, creating a huge earthquake, mega tsunamis, injecting miles and miles of dust debris up into the atmosphere, distributing itself globally in such a manner that it blocks sunlight out. You could have had darkness for months at a time. This is enough to shut down photosynthesis. That's the top of the food chain, and that just has a trickle-down effect.
If Becker's theory is correct, this impact could have wiped out most life on Earth, since it was concentrated on one continent and one ocean. An extinction event of this magnitude would have allowed for complete evolutionary change, thus paving the way for the dinosaurs to evolve.
It was only because the Permian-Triassic extinction event occurred, and what I consider to be somewhat attributed to this impact event, that the dinosaurs were able to evolve.
Little geological evidence remains of the Permian-Triassic extinction. There are very few 250-million-year-old rocks left on Earth because they've been recycled by plate tectonics. But Becker says she's found traces of the actual impact crater in northwestern Australia. The Permian-Triassic extinction, known as the Great Dying, was the biggest extinction event in the history of planet Earth. 90% of all life perished 250 million years ago. More creatures expired during this period than the KT extinction that killed the dinosaurs over 185 million years later. The cause of the Permian-Triassic extinction has gone unsolved. But now, research scientist Luann Becker and others think an asteroid caused the event. And they've uncovered a possible impact crater buried under sediments offshore of northwestern Australia.
We believe we found a very good candidate for what is the impact event itself. It's much older, it's a lot more complicated and a lot more geologically processed. It's not a perfect circle anymore. It doesn't look like a bullseye. Most of the Permian rocks have been subducted and they're long gone or eroded away.
The evidence for an impact there is marginal and highly controversial.
Some scientists are skeptical that Becker has found an impact crater from the Permian-Triassic period.
No good crater has been found to match the Permian-Triassic age. There was a claim of a structure off of the west coast of Australia, but it's not as clean and as clear as the KT crater. We don't have a smoking gun.
But Becker claims she has found the smoking gun. What's more, she and her team have traveled to Antarctica, Australia, Africa, and Japan, where the oldest rocks on Earth exist. They claim to have found 40 impact tracers. These are extraterrestrial mineral fragments recovered from rock layers dating to the Permian-Triassic period.
We have found what we consider to be little bits and pieces of impact debris which literally looks like what we'd find if we were looking at a meteorite. It's possible for some of the impact meteoritic debris to fall back down and get preserved in the rock layer.
What hasn't been recovered from the Permian-Triassic rock layer is iridium. It's the meteoritic substance that helped to convince many scientists that an asteroid impact caused the extinction of the dinosaurs 65 million years ago.
Colleagues want to try to get real nitpicky about, well, you should have found iridium too. Well, we're not finding iridium in some of the places we would expect to find it, like in some of the commentary material that we brought back. So what's the explanation for that? It's just that there are different bodies and they're not all the same.
Although Becker hasn't found iridium, she has procured chromium in rocks from Antarctica. Like iridium, chromium is just as rare and is more abundant in space rocks. So, did an asteroid actually cause the Permian-Triassic mass extinction? Or merely help it along? It appears that life was struggling to survive 250 million years ago. The planet was undergoing severe volcanism, which was choking the atmosphere.
One possibility is that a large volcano in Siberia, which was sitting atop an enormous coal deposit, may have released a lot of greenhouse gases into the atmosphere, such as CO2 and methane, which would cause a massive die-off among marine organisms, and also an enormous amount of global warming, which would have been bad for the terrestrial animals as well.
When you go back and look at what does correlate with these other extinction events, virtually in all the cases, there's evidence of a mass volcanic episode at the same time. And all of the mass extinction events, including the KT, are strongly and intimately associated with these volcanic eruptions. The extinction events may have happened anyway, but then this damn meteor came in and really mucked things up. So it was a double whammy.
Becker claims that volcanism alone couldn't have caused the Permian-Triassic extinction, and she says she has even more evidence to prove it.
We have found, I think, some of the best proxies for what we consider to be impact tracers. This includes shocked quartz in multiple locations in and around Australia and Antarctica. Glass that has seen pressures that are far beyond what you can even think about happening, geologically speaking, on the Earth. This could not have been mimicked by some kind of volcanic event. It has to be something that was produced by an impact event. And I think that when you have that kind of direct evidence, that's as good as it gets in this business.
The scientific community is still debating whether an asteroid impact helped trigger the Permian-Triassic extinction 250 million years ago. But space rocks aren't the only objects that can cause cosmic upheaval. In fact, our own Milky Way galaxy is currently involved in a multiple galaxy collision. Imagine you're a galaxy cruising through space. The traffic may seem light, but at any moment, you could be involved in a head-on collision. Cosmic crashes like this happen all the time, particularly when galaxies get too close to one another.
Galaxies have interacted, they've collided, they've merged, they've ripped each other apart, and it's still going on today. So galactic collisions have always been a part of the life of a galaxy, and they always will be.
Research scientist Michelle Thaler knows how violent galaxy collisions can be, especially when they involve multiple galaxies. At this very moment, NASA's Spitzer Space Telescope is witnessing the ultimate pileup. 4 supermassive galaxies colliding on a cosmic freeway, approximately 5 billion light years away from Earth.
They're all coming together now at millions of miles an hour, and they will merge together. So we found an absolutely titanic collision of galaxies. You can think of most galaxy collisions as being like, little compact cars maybe piling up, a small collision on a highway. But in this case, we're seeing maybe, 4 18-wheelers colliding together head-on. And in the process, billions of stars are being just scattered away from this galaxy.
This violent collision is still happening. When the impact is finally over, the 4 will be jumbled together to form one beastly galaxy, 10 times the mass of our Milky Way. It will be one of the largest galaxies in the entire universe. And this is just one of many multiple galaxy collisions. The Milky Way will eventually merge with our neighbor galaxy, Andromeda, which could prove to be a spectacular collision. But right now, our galaxy is actually colliding with 2 smaller galaxies, which is causing quite a stir.
There's 2 galaxies right now that are actually relatively small galaxies, but they're colliding with the Milky Way right now. One is called the Sagittarius dwarf because we see it near the constellation Sagittarius, and another is called the Canis Majoris dwarf galaxy. Now, the second one, the Canis Majoris dwarf galaxy, is very interesting because it appears to have been sort of drawn into the Milky Way and ripped apart as it orbited around the center of the Milky Way. So we can actually see streams of stars all going around together that are the remnants of this poor little galaxy that got ripped apart.
Galaxy collisions produce billions of stars. But can these stars also collide?
The space between stars in our galaxies is absolutely huge. If the sun were about the size of a basketball, and I'm here in Los Angeles, then the nearest star would be about the same size star in New York. Imagine a basketball in New York. There's so much space between stars that stellar collisions are so rare.
Although rare, star collisions can occur where stellar objects are formed in dense clusters.
We've seen examples where in a cluster of stars, one star seems to be more massive than the other ones, younger than the other ones, and spinning much faster than the other stars that it was born with.
These young stars are called blue stragglers. They occur in unusually dense groups of stars called globular clusters.
These are called blue stragglers because they seem to be younger. They're aging less quickly than the other stars of the clusters. So it's very possible that these are caused when 2 stars actually merge together. As these stars approached each other, they spun each other up with their gravity. And so you get this very fast rotating, large, bright star.
And star collisions are not mild galactic fender benders. They can be quite destructive.
They would sort of loop closer and closer together, going faster and faster. They'd probably get to many hundreds of thousands, if not millions of miles an hour. And they'd begin to rip bits of each other off as they came close to each other. So a stellar collision could be an extremely dramatic, violent thing to watch.
Eventually, if the mass transfer happens enough, over enough time, the orbits will shrink, and those 2 stars will get closer and closer together, and they could eventually merge, forming either one single giant star or eventually collapsing into, say, a neutron star or a black hole.
Whether they're star and galaxy mergers or asteroid and comet impacts, cosmic collisions will continue to happen as long as the universe exists. By gaining knowledge about these uncontrollable events, we can reach a better understanding about the origins of the universe and possibly predict its future.
Cosmic collisions have been a major factor shaping the evolution and history of the planet. Earth wouldn't be here without them. The chemicals that life needs to get started with came out as a result of these impact processes. So this has actually been a very important factor in the history of life on this planet.
Cosmic collisions are responsible for things as varied as asteroid impacts, galaxy mergers, formation of giant stars. They're obviously key to our understanding of the phenomena in the universe.